Analysis of RF device fingerprinting using convolutional neural network. Abstract: the authentication of devices and identification of unauthorized signals has been difficult in many scenarios. In this paper, a method for identifying a specific device among a range of similar devices is discussed using the techniques of convolutional neural network. The approach is to use radio fingerprints as samples for the identification process. The variability caused in the manufacture of these wireless transmitters serves as a unique feature, creating repeatable signatures for a particular device. These signatures are used as fingerprints for identification and verification. A framework is then developed for training the convolutional neural network using complex baseband error signals in time domain for varying signal-to-noise ratios, SNRs. Keywords: convolutional neural network, device fingerprints, error signals, hardware variability, trained data, radio frequency. Introduction. In the previous couple of decades, there has been an improbable growth within the application of Internet and the devices connected to it. However, the security and privacy of these billions of devices could be a preponderating concern within the Internet of Things, IoT, network. Any device that has network property is vulnerable to attacks. Information gathered by such devices are prone to attacks like ID spoofing by intruders. Almost all of those devices have restricted memory capacity and computing power, that makes it troublesome to use complicated cryptographic algorithms that need additional resources than the devices will give. Therefore, there is limited authentication or authorization. The device identification is the process of relating a received signal to a device employing the radio frequency, RF, features database of certain known transmitters. The most efficient identification systems should be ready to correctly determine emitters, however should even be quick, robust to ever-changing environments, and simply and quickly adjustable. The speed of such systems is particularly essential during a military setting, wherever the system is also accustomed to give early warning. Moreover, in environments where there can be constant changing of channels or when variations occur in the transmitted frequency, modulation schemes and bandwidth, or if there occurs presence of other transmitters, it is vital that the developed system works well under these conditions. However, ought the system have to be compelled to be tuned or changed in order to accommodate a brand new. Preetha Basu, Professor, Electronics and Communication Engineering, TKM College of Engineering. Carry code, Kalam. Surroundings: such changes ought to be easy and economical to implement. In several mission-crucial eventualities, issues in unauthorized transmissions, authentication of devices and ID spoofing are major considerations. This work on device fingerprinting solves the eventualities by learning device-specific features of the transmitters in an exceedingly pre-deployment training stage, that is then exploited throughout actual network operation. Thus, for general purpose use, any device fingerprinting approach must be computationally straightforward once employed in this field. It is for this sole reason, machine learning, ML, techniques, specifically, the one convolutional neural network, CNN, is proposed and through an experiment demonstrate its radio identification performance for a set of devices. RF.Fingerprinting aims to spot transmitters based on the device SPICY.C features found in their emitted analog signals. The main advantage here is the minimal pre-processing performed on the baseband signals that is downconverted, which is then sent for identification to neural networks. These features are caused due to the hardware variability within the analog transmitter parts of the device. For this reason, a study on RF.Fingerprinting supported by applying of deep learning classy.cation strategies is performed and its feasibility is demonstrated. Owing to the huge success of deep learning ways at advanced classy.cation tasks in image and speech recognition, this method tend to apply convolutional neural network, CNN, to the RF.Fingerprinting drawback. 2 related work. A traditional identification system can be represented as in Fig. 1. This system consists of an RF module, followed by the data collection module, signal processing module, feature extraction, clustering techniques, and finally the identification and verification module 1. The RF and data collection modules focus on pre-processing the analog signal obtained from the RF receiver, converting it into the digital domain, before the signal processing operation occurs. The stages involved in the signal processing phase mostly deal with the features that need to be extracted in the next stage and primarily include demodulation and filtering. Once all the necessary processing is done, all the data is brought onto the feature extraction stage, where predetermined features are extracted. The obtained features are further used in clustering and identification purposes. Fig. 1, a traditional identification system. Normally, the RF fingerprint of a device, termed as the electronic signature, occurs due to the variations in architecture and RF components employed by manufactured and certain non-idealities seen in the device's hardware too. Moreover, RF fingerprints usually does not depend on the signal transmitted or on the data present in that signal. The major success of the traditional identification systems was due to the selection of features which symbolizes a certain portion of the RF fingerprints of a set of devices 3. Often, the features employed in the traditional identification systems either come from the steady state or the transient portions of the received signal. The methods used to analyze the steady state signal are a lot diverse and include usage of modulation-based approaches 4, wavelet-based approaches 5, cyclostationary-based approaches, preamble-based approaches 6. One of the popular wavelet-based approach, termed as the dynamic wavelet fingerprint approach, utilizes wavelet transforms on the steady signal in its time domain 5. The features generated in the modulation domain calculate the error between the ideal demodulated signal and the transmitted signal 4, whereas the preamble-based approach analyzes the features of the preamble extracted, namely its periodicity 6. The cyclostationary-based approach analyzes the salient cyclic features present in a signal. The transient or steady-state techniques are made in use to extract features which are used in combination with the clustering techniques for identification and verification of specific emitters 7. The most commonly used algorithms include k-nearest neighbors, KNN, support vector machines, SVMs, 8, along with principal component analysis, PCA, or linear discriminant analysis, LDA, if required. Furthermore, there can be variations in the frequency domain and time domain features according to the channel conditions and noise, and which can henceforth be impacted by various channel impairments like the multipath 9. Even though it is more practical to use the features that are extracted from the received signal that fall under its steady state portion, there are certain limitations associated with the expert features that are used for the detailing of the steady state signal. For example, wavelet functions greatly impact the wavelet-based techniques. For cases that lack a predefined preamble, the preamble-based techniques fail 10. Furthermore, methods used to analyze the cyclostationary features of some particular signal are normally seen inconsistent when the phase or frequency uncertainties are present and often consumes a lot of time to compute. Finally, there are numerous limitations involved in the classification or clustering algorithm of traditional identification systems. Many classification or clustering algorithms such as neural network classifiers, KNNs, and SVMs demand to input the cluster number from the user or usage of an iterative method to calculate the required number of clusters for the provided dataset 11. Other than for a cooperative environment, the number of clusters, devices, cannot be known earlier and is subject to change, causing limitation in the identification of anomalous devices and their behaviors. Some training has been carried out on a probabilistic neural network, to identify 8 IEEE 802.11b Wi-Fi cards making use of the transient amplitude signal of Wi-Fi transmissions 12. Also, various techniques involving wavelet and Hilbert-Hwang 13 transforms have been experimented for studying the success of RF. Printing. The major drawbacks of traditional identification approaches involve the extraction and the usage of expert-defined and predetermined features. The initial step for the design of a traditional identification system involves the need of an expert to characterize the quality features under consideration. These defined features remain accurate only over a certain range of parameters and often require consistent and detailed measurement or evaluation in order to facilitate quality identification performance. 3. Proposed method. The project consists of two phases, i.e., a training phase and an identification phase. In the first phase, the CNN is trained using raw IQ samples which are collected from each transmitter in order to solve a multi-class classification problem. In the identification stage, those samples belonging to the unknown transmitters are fed as input to the trained neural network, and identification of transmitter is done based on values observed at the output layer. A. Data generation. The sequence of binary data samples are generated based on particular number of samples for each device, then it modulated with the help of quadrature amplitude modulation, QAM. After the modulation, the signal are converted to orthogonal frequency division multiplexing, OFDM, data by taking inverse fast Fourier transform. These OFDM signal generated by specific range of symbol to noise ratio and 64 FFT size and 52 subcarriers, and pilot is added before conversion of OFDM modulation. Similarly, we are generating the input for all devices and saving it in a .mat file and loading it for testing. B. Convolutional neural network. The network consists of 3 convolutional layers and 3 dense layers. The goal was to first understand stacking of layers and the functions and operations of the various layer. The most challenging task in building the CNN network is to identify how many layers to be defined, number of filters needed in each layer, the filter sizes, values to be given for padding and number of stride. These are not standard values and the network complexity depends on the type of data and the processing required. A lot of effort needs to be put on experimenting with various parameters and finally identifying the exact combination of these hyperparameters that defines the data well. The input given to the CNN is a windowed sequence of raw I/Q samples with length 4320. Further, each of the complex values are represented as 3-dimensional real values, which results in the dimension of the input data to be to 1 times 4320 times 1. The first parameter under consideration is the number of filters to be used in the convolutional layers. It was observed that the number of filters within a range of 30 to 256 could provide somewhat similar performance. However, as the number of filters increases, the number of computations also increases. Hence, the first convolutional layer was made of 128 filters, whereas the second and third had 32 and 16 respectively for balancing the performance and maintaining computational cost. But, the filter size in all 3 convolution layer was set as 1 times 1, since larger filter size does not provide any significant performance improvement in the network. Moreover, on increasing the number of convolution layers from 3 to 4 shows no improvement in the performance of the network, which demands continuation with 3 convolution layers. This is followed by a max pooling layer of dimension 1 times 1 and having stride 2 times 2. This layer helps in the extraction of sharp features by reducing the dimensionality through downsampling through reduction of parameters, which in turn helps in low computation in the network. The number of neurons in the dense layer is 10 since 10 samples from 10 devices are taken for classification. It is found that increasing the number of neurons does not improve the performance. In the parameters selection, it is observed that increasing the number of neurons increases the complexity and in turn makes the training slower. One of the major problems during network training is overfitting, during which the network weights gets tuned so well to the training examples while the network fails to perform well when given the unseen data. Thus measures need to be taken to alleviate the problem of overfitting. A dropout layer is used, whose main function is to drop out a set of activations in that specific layer by setting them to 0. By doing this, it is made sure that the network is robust and ensure that it does not get too fitted to the training data. A dropout rate of 50% is used at the dense layer. For results, the work deals with training of 10 devices. The transmitted signal from each device is modeled with the help of the MATLAB software. On obtaining the error signal from each device, it is fed onto the CNN as input for training. A total of 200 samples are taken for the training dataset, 20 for each devices, and are classified into 10 categories, which helps in the identification procedure. Random samples from the training set are given as input for identification process. The important function during training is finding right set of weights that fit the data well and classifies devices correctly by reducing the error at the output layer. This is done using optimizers, and here, Atom Optimizer is employed. The output predictions for two MAT files belonging to device 1 and 5 respectively are shown. As the first input MAT file, belonging to that of device 1, is fed onto CNN and training is done, a plot of mini-batch accuracy versus number of iterations, equals 50, is done as shown in Fig 5.2a. It is clear on plotting that as the number of iterations and learning rate is increased, the identification becomes more accurate. As number of iterations are increased, it is observed that the accuracy increases and the loss decreases, Fig 2b. The identification is made as device 1. When another input data, belonging to device 5, is given, it is identified to be of device 5 and is shown in Fig 3a. The improvement in accuracy and loss as the iteration progresses is further analyzed from the obtained results as shown in Fig 3b and Fig 3c. The light and darkened lines indicate the unsmoothed and smoothed curves respectively. If it is smoothed, it is less noisy and the trends can be easily spotted. Fig 3c improvement in accuracy and loss, input 2. When a random unknown signal is given as input to the CNN, it does not find any match with the already trained dataset and the MATLAB would plot the input data, but the CNN fails to identify the device to which it has correlation and hence displays it as invalid instead of classifying it into the 10 class of devices. This helps in authentication of unauthorized signals. Fig 4, unknown signal unidentified. The method demonstrates the identification of devices whose transmitted signal samples are present in the trained dataset of CNN. Any other random signals provided as input would be unidentified. This technique is used in military for applications like early warning systems, device tracking, and device location. Conclusion. There arises the need for novel techniques that can identify devices and also help detect malicious activity. The existing approaches of device fingerprinting require expert feature extraction and are not capable enough to train large data sets. Hence a radio fingerprinting approach is studied based on deep learning CNN architecture to train the input samples. This approach enables learning features embedded in the signal transformations of wireless transmitters, and helps to identify specific devices. Furthermore, it is clear that this approach of device identification using CNN outperforms traditional machine learning techniques such as logistic regression and SVM for the identification of fewer devices. Finally, it is experimentally validated that the performance of this design improves on increasing the learning rate and the number of iterations. The future work revolves around increasing the robustness of the CNN architecture so to allow scaling up to correct identification of 1,000s of similar devices. Another challenge is realizing the right balance between training time and the classification accuracy. The classifier used performs well on limited number of devices, however, to identify large number of devices, in the range of 1,000s, it may require some major changes in the architecture and the need for new optimum parameters.